So hi, and welcome to today's alumni lecture for the University of Utah Alumni Association. It's my great pleasure to be able to present to you today, and thank you very much for coming today. So the topic of my lecture today will be on computing infrastructure for the future of our networked world. And before I get too deep into the talk itself, um, I'd just like to introduce myself a little bit more. My name is Rob Ritchie. I am a professor in the School of Computing, which is part of the College of Engineering at the U. And I am one of the co-directors of the Flux Research Group, which is a research group that has about a dozen staff members, about twice as many students as that. So it's a pretty sizable research group within the School of Computing. I'm a research associate professor, which means that as a research professor, it means that my duties on campus are mostly around research and advising students, and less so around classroom teaching. But I've been around the U for a very long time. I got my bachelor's degree from the U in computer science in 2001. I got my PhD in 2010, and I've just been around ever since. So I've been around campus for quite a while. So the statement that I have on the slide right now, I think, is one that is probably not particularly surprising or controversial. So we depend on computers, phones, and other devices more and more each year. The very fact that we're doing this lecture in an online format, I think, is a good evidence for that. I'm sure that, especially over the past couple of months, a lot of us have spent a lot more time doing our work online, spending time, with family and friends online than we're used to. And this trend is one that's been going on, however, for quite a while, right? Um, but in order to be able to do these things on our computers, on our phones, um, there's a lot of computing and network infrastructure that underlies all of these things that we do. And so that's what I'm going to talk about today. So this talk is going to have three parts. First, I'm going to talk about what I even mean when I'm saying, computing infrastructure. Um, and then I'll talk about, how this infrastructure is changing and what this means for the future of how we go online and the kinds of things we do online. And then I'll give you an update on some of the things that are going on campus about how the U is actually working to help enable some of these changes and enable the future of our networked world. And my plan is that what I'm going to do is that I'm going to pause in between each of these three sections because I want this to be fairly interactive. And you can type in questions into the YouTube chat, and those will get relayed to me. And so I'll try to take questions after each one of these three sections, and I'll try to give you a little bit of warning so you have some time to compose your question and type it in. So let me start by just asking what it is that I mean by computing infrastructure, right? And how is this something that we use every day? And I'm going to start with an example that I think is probably very familiar to most of us, right? Which is the experience of using, like, let's say, the Facebook app on our phone, right? So you think of this as having Facebook on your phone, right? That's where it's displaying your friends list and your feeds and their posts and that kind of stuff. It's how you interact with Facebook. Um, but in a real sense, Facebook and many of the other services that you use, right? Like, whether that be, Google or Zoom or various online drive kind of platforms or learning platforms. In a very real sense, these things are services that are really too big for your phone, if you will, right? So in the specific example of Facebook, Facebook is a service, right, that stores lots of pictures that you've uploaded to it and that your friends have uploaded to it, and lists of friends and posts and comments and all these kinds of things. And so really this is a service that is running somewhere other than your phone and that you're accessing from your phone. So in reality, the picture looks a little bit more like this, right? You have your phone that is communicating with the Facebook, the service. Where does Facebook, the service, live? Well, it lives on a set of servers, right? Which I've indicated with a little stack of servers icon on here, and that's where a lot of the data is stored, where a lot of the algorithms that decide what to show you, et cetera, run. Um, and so the computing infrastructure that I'm talking about is this part that sits underneath the services that we use on a daily basis, and the apps that we use on a daily basis, whether or not we even know we're using it. So Facebook itself, of course, is a really, really big service, right? So it's not just sitting on one set of servers in one data center. Facebook is actually in data centers all around the world. And these are gigantic data centers with lots and lots of servers. Um, and often when we talk about a service that is provided by infrastructure that we don't control, that is not visible to us, that is in some undefined and maybe mysterious location around the world, we call this the cloud, right? So often when someone says that they're putting something in the cloud, this is what they're talking about. Now, of course, my phone itself is not directly connected to these Facebook data centers, right? My phone is actually connected via Wi-Fi or via the mobile, also known as the cellular network, to some kind of base station or tower or access point. And this is also part of our internet infrastructure. That tower and the radio communications that we use to talk to that tower. And then once it gets to my mobile phone provider, the data that I'm sending to and from Facebook, actually still has quite a long distance to go, right? It actually has to go through other networks that we call internet service providers or ISPs. It needs to go through what we call internet backbone networks. And there are a lot of services and devices inside of these networks that are making decisions about, oh, okay, well, if I'm trying to get this particular bit of information to a Facebook server, right? How do I get from this cell tower to a Facebook server, right? And if Facebook has data centers all around the world, which of those data centers am I reaching? And so, what I have on this slide, looks like a fairly complicated diagram, right? But of course, it's actually a great oversimplification of what the internet infrastructure looks like. And so it is this infrastructure that I'm going to be talking about in the talk today, and the parts that are invisible underneath what we usually think of as the services that we use. And I'm going to be specifically focusing on the cloud portion and on the radio access portion. So I just called this infrastructure the invisible parts, but of course it is actual physical infrastructure, right, that does actually exist someplace and is not invisible, right? It may be in somewhat obscure places, but it really is out there and you really can see it. So I thought it might be fun to kind of look at some pictures of what this stuff actually looks like. So this picture is provided by Google. This is a Google data center. This one happens to be in the Netherlands. And as you can see, right, it's got some big gray warehouse type buildings. Those are full of computers. It's got a bunch of other equipment around it. Some of the blue equipment that you can see is probably related to providing power to those computers, to providing cooling to keep them from overheating. And you can kind of get the sense of the scale by looking at, how tiny the cars in the parking lot in this picture really look, right? So these data centers are just massive, massive things. Google has probably, like, let's say tens of data centers this size in the United States, maybe another tens or so of them in Europe. And other numbers, all throughout the world, in Asia and South America and Australia and Africa. And of course, Google is not the only company that has data centers like this, right? Other companies like Microsoft have them. Companies like Amazon, through their AWS platform, have many large, gigantic data centers. And so, overall, there are probably hundreds to thousands of such data centers all around the world. And this is where a lot of the physical computing infrastructure that we are using every day actually lives. Now, normally these are very high security facilities, right? So you don't actually get to go inside them. Thankfully, Google has also provided us some pictures with what some of their ones inside look like. So this is a picture from inside of one of their data centers that's in Iowa. Um, what we're looking at here is the inside of this very large warehouse type space, right? And you can see these rows and rows and rows of computer servers. They have little flashy lights, like you would expect, a computer to have. Um, so when you do a Google search, or when you go and read your Gmail, uh, that data is being served up from servers that are in a room like this one, maybe even this specific room. So let me give you a little bit more of a schematic picture of what is in a cloud. The physical picture is useful, but I think it's kind of useful to have kind of a higher level understanding of what's going on inside. So a cloud data center has three main types of resources in it. One of those resources are compute resources. So these would be like the processors that are in your desktop or laptop. There will be graphics processing units to do things like process photographs and videos. There'll be special accelerators that are designed for machine learning tasks or other artificial intelligence tasks. And those comprise the computing part of a cloud data center. Then there'll also be lots of storage. And again, this is not entirely unlike, the hard drives that you might have in the computers that you own, right? Some spinning disks, some flash and SSD drives that are storing, all of those information about who your Facebook friends are and all the pictures that you post to Google Photos. And then lastly, of course, there's the network that is connecting all these servers together and are also connecting it with the outside world, right? So that it can, so that your phone can reach these services, or your desktop can reach these services from anywhere that it is in the world. So using these three basic building blocks, we build a lot of services, then a lot of different services on top of it, right? So for example, I've got icons here representing a video conferencing service, not unlike the one that we're using right now, where the compute part might be used for processing the video, doing encryption, making sure that everybody is receiving a stream that is the right quality for the device that they have. The storage component may be used to actually store a copy of the video so that it can be put up online later. And then, of course, the networking part is used, to take the video from me and broadcast it out to all of you. You might build on exactly the same cloud, on top of exactly the same building blocks at the same time, a photo sharing service where now the storage is being used to store the photos that are associated with those files. The computing is being used to process those photos, to do things like index them. Again, the network is used to access them from anywhere. And so the idea behind cloud computing is you use these three basic building blocks, and that you have a whole bunch of different applications that are all built on top of them and running in the same data center at the same time, using just the resources that they need at the time, right? Everything from e-commerce shopping kinds of websites to gaming services to things like YouTube, to just plain old websites. And the public cloud, such as provided by Amazon's cloud services, and Google and Microsoft have similar offerings, are one where developers and companies can come and rent time and space and storage on these computers and develop their own applications, right? Run the services that back up their own apps. And clouds are terribly complicated things, but this is kind of the basic, these three basic services, and you build a whole lot of applications that are sharing the same infrastructure on top of them. So I'm going to switch from the cloud part of things to the mobile wireless access part. And I'll say that in just like 2 or 3 minutes here, I'm going to be taking a break for questions. So if you have any questions, now would be a good time to type them up, to start typing them up. So, not all of this infrastructure is necessarily in places that are, far away or obscure, right? And in particular, the mobile network, the cell phone network, has portions of it that are all around us. So these are actually some pictures that I just took in my own neighborhood, which is right near the U campus. Just on a walk through my neighborhood the other evening, right? So the thing that you see on the left-hand side, is an example of a cell tower. It's not a particularly beautiful cell tower, but there it is. And so when your phone is connected to the mobile network, it is talking to the antennas that are on the top of a tower like this, or you may have seen the kind of rectangular white patch antennas that you'll see on tops of tall buildings as well. Those are also used for the mobile wireless network. Once you get in, once your phone talks via radio to that cell tower, that traffic needs to get out to the rest of the internet, right? And so that's going to go through cables or fiber or something like that, that in many cases is run underground. So on the right-hand side, you can see this is a communications access hatch that just happened to be in somebody's yard. And it is providing access to the wired portion of the mobile wireless network, right? So this is connecting that cell tower off to the rest of the internet, and there's probably some equipment that we could get to if we were to open up that panel. Of course, also, in many neighborhoods, we put our infrastructure above ground. So the thing on the right, we often call it a telephone pole. A utility pole is probably a more accurate name. This particular utility pole has on it plain old telephone lines. It also has fiber on it that's owned by Google Fiber. It also has cable on it, so like that's used for Comcast cable TV and or cable modems. And on the left-hand side, what we're seeing, this is a picture of a cabinet that's owned by Google Fiber. So again, underground, there's probably some access to some fiber under there, and then that cabinet probably contains some kind of network switch in it. So this is a good point for me to take questions, and I see that I've already got some. So the first question that I have is, are there any large data centers near the U? So actually there are. The U actually owns a very large data center that is down near, if you're familiar with the 9th South exit from I-15, there's a very, very large brick building. It's actually the entire length of a city block down there that used to be, if you remember back far enough, it actually used to be the local Coca-Cola bottling plant. But now it is a data center that's owned by the U. There are a number of small data centers. There's even data centers in the downtown area that are even in little parts of office buildings. And then there's a number of data centers that are down kind of near the point of the mountain area in between Salt Lake County and Utah County. So the most prominent one down there is owned by the NSA, the National Security Administration. And it's actually, I think it's up there with the biggest data centers in the world, actually, and you can see it up kind of on the mountain if you're on I-15, right just west of Point of the Mountain. So another question that I've got is, how much of the cloud infrastructure is private versus public? It's actually a good question. I don't know the exact numbers on that. What I do know is that the public cloud, by which we mean, the portion of the cloud that is offered, as a service that basically anybody with a credit card can come rent space on, is just growing at enormous rates, like all the time, right? A very, very large fraction of the services that you use all the time, right? Netflix and Amazon streaming services and stuff. A lot of these things use lots and lots of infrastructure in those clouds. So I don't really have a number to give you on what like the fractions are, but I can say that I think the public version of the cloud is probably growing quite a lot faster than the private. All right, so I think I'm going to go on with the next section of the talk. If I didn't get to your question in this part, there'll be another few chances to ask questions. So the next thing that I want to touch on is, how is this infrastructure changing, and kind of what is this going to do in terms of how we use the internet and kind of what our world looks like in the future. So one big trend that we see is that we have fewer wires, right? We have more things that are connected to wireless networks, right? So like Wi-Fi, like the cellular telephone network. And these connect, of course, over RF or radio frequency. Um, Radio frequency is split into a bunch of different frequencies. So if you're familiar kind of with the image of like a prism splitting light into a bunch of different colors, right, where each of those colors is a different wavelength of light. The radio frequency spectrum works basically the same way. There are a bunch of different frequencies of radio waves, and they have different properties. So, for example, things that are higher frequency um, provide faster speeds. You can transmit more data. But on the other hand, they travel more. The distance that they can travel is shorter, and they don't do as good a job, doing things like penetrating through walls, right? So, for example, if you have Wi-Fi at your home, you've probably noticed, right, that different rooms in your house, right, get different strengths of Wi-Fi signal in part depending on the walls that are between you and the access point. And so one of the things that's happening is that we are looking at using higher and higher frequencies in order to enable those faster speeds. Because that these reach shorter distances, this means that we need to have more places, more access points, more base stations. So, for example, the reason that there's probably that new base station that cell tower that I took a picture of in my neighborhood that's probably gone up because it's serving a smaller area than is served by the lower frequency older equipment in my neighborhood. Another thing that we're doing is we're allocating more and more of this wireless spectrum to devices that we might think of as consumer facing. So this rather colorful diagram that I have in the right hand of this picture is showing a little piece of the allocation diagram for RF spectrum in the United States. So in the United States, the FCC, Federal Communications Commission, is the one that controls which part of the spectrum is used for what purpose. This is a little tiny picture of a giant, like wall-sized diagram that shows how it's spread out in the how it's allocated in the United States. And what we see is that as we use more things like Wi-Fi and Bluetooth and mobile cell networks, and we try to attach more devices to them, we need more allocations. And so there's a lot of changes going along with how these things are allocated. So these are policy decisions at some level, but they actually end up affecting our lives in a lot of ways by making the spectrum available. And an example that I can give you is that you may remember several years ago, we went from the old style over-the-air TV transmissions, which were analog, to newer, higher quality digital over-the-air TV transmissions. And one of the motivations for doing this is that those old TV transmissions, the analog ones, used tremendous amounts of spectrum. They were not very efficient. The digital ones transmit better quality signal and less spectrum. So that means we've freed up a lot of what is called TV white space that now is potentially useful to connect new kinds of devices to our wireless networks. Another example for how for the way that this is changing is that we're getting better at sharing spectrum between multiple uses. So I can give you an example. There's a gigantic chunk of spectrum that is allocated for naval radar. As you could imagine, even in a place like Utah, the naval radar does not see a lot of use, right? However, the government still does have the right to use it if they choose to. And so figuring out more useful ways to share that spectrum where, the primary user gets priority access to it, but if they're not using it, other people can use it for other purposes. This is another major area of research these days. So what does this mean for us? Well, it means that we're going to have more and more devices that are connected to wireless networks that are potentially mobile, right? That can be used in a variety of different places, and it means that the connections, the speeds of those connections that they're able to have are much faster because we have higher frequencies, more spectrum allocated to it, and more efficient use of the spectrum that we do have. So at the same time that we're deploying more and more stuff through wireless mechanisms, we're also putting more and more fiber optics around to connect our neighborhoods. So if you're not familiar with fiber optics, essentially it's these thin pieces of glass fiber, as shown in the figure on the right here, and then we transmit data on them with light. And fiber is pretty amazing because you can transmit just tremendous, gigantic amounts of information over a single fiber by using different frequencies of light, the way that you would use different frequencies of RF transmission, and it's extremely reliable and it's relatively cheap. So this means that we have faster speeds available to our homes, right? So in many neighborhoods in Salt Lake City, you have options like Google Fiber, like Utopia, some of the in some places CenturyLink or Comcast offer you fiber to the home, and to our offices. And one of the uses for fiber is that it actually connects us across continents, right? There are 1,000-kilometer fiber runs that go underneath the oceans, right? That actually connect us to Europe and connect us to Asia and connect us to South America. And so again, along the in a similar way to the way that all of these wireless innovations are providing us with faster connections, we're just getting faster and faster speeds to our homes and offices. And it's kind of cliched to say this, but communication wise, right, the world is a much smaller place than it used to be, right? We can get very good quality communications to places on the other side of the earth very, very easily and cheaply now. I'll just give you another heads up. I'm going to go through this slide and then I'll take questions again. But so what does this mean for us? Well, so what it means is that we can support a lot more devices that interact with the physical world. To give you an example, right, we have in my house I have a sprinkler timer that connects to the internet and uses a weather service, right, to not run the sprinklers when it knows it's going to rain in the near future, right? Or to, give the grass extra water when it knows it's going to be a particularly hot day. And so this is a case where by connecting to the internet and by using some of that computing infrastructure, right, I have a device in the physical world that interacts, more completely with the physical world. We also have apps that have access to a lot more data than they used to. So just to give you an example, right, some of you may have one of these video doorbells at your house, right, that has a video camera on it. It may have access to, sort of not only that video stream, but to photographs of the people that you're expecting to come to your house, right? So that, when somebody shows up at your front door, you can compare that video against, the pictures of people that you're expecting to show up, and it can tell you, who's there, or, whether you expected them to be there or not. And this is just a tremendous amount of data that is just not possible without those high-speed internet connections and without those high-speed processing that goes on in clouds. And we have much clearer communication between these things, right? If you've used video calls in the last couple of months, if you had used video calls a decade ago, right, they were much lower quality. And we just have more services and more apps that are just available kind of anywhere you are, right? It's a lot of us have been able to work at home because we have so much available through this network infrastructure. One thing that I do want to bring up before I move on, though, is that as a computer scientist and as a society, as society in general, one thing we do need to think about, though, is that this future is not, evenly distributed, in the sense that, there are some neighborhoods, there are some areas that have very good internet access and that have very cheap, plentiful cell phone service. And we have other neighborhoods and other geographic areas where access is spotty, right? Or it's more expensive. And I think, something that we need to think about as we continue to build this infrastructure and to build apps that depend on it is that, we need to make sure that, if, to the extent that we all depend more and more on these services, that they're available in a utility kind of fashion, right? To everybody everywhere, so that we don't leave, certain groups behind. So I think this is a good point to take some other questions. Okay, so somebody asked, what are the pros and cons of fiber internet? So this is a really good question. For the most part, I would say there are pros and not a lot of cons. Essentially, fiber is the amount of data that we can theoretically push through a fiber is at this point far more data than we even know what to do with, right? So if you get a gigabit, connection, fiber connection at your home, that actually represents only a very small fraction of what's possible to put on fiber, and fiber, somewhat surprisingly, is actually relatively cheap to deploy as well. So in general, it offers you pretty high speeds. It's pretty low. It's pretty reliable, and there are not really a lot of downsides to using fiber for internet. Okay, so another question. It's a very good question. I'm glad I got this question. With the increasing volume of data available, how are we dealing with the privacy aspects? So this is a really big part of our networked world, and it's something that I think we all both need to pay attention to individually, and that needs to be paid attention to by our lawmakers and our policymakers. So, a kind of a flip description of what the cloud is that it's someone else's computer, right? So it's taking, I used to, years ago, have a hard drive in my desktop computer, and I stored all of my photos that I took on that hard drive. Now I store them in Google Photos, so they're in the cloud. So the trade-off that I've made there is that the photos that I store in Google Cloud are that service offers a lot of organizational things for me, right? It'll catalog them based on who's in the picture. It'll catalog them based on when I took them, where I took them. It's very easy to share them, right? They're available on my phone and on my desktop, and I can send them pretty easily to my family. However, the flip side of that is that I am placing a whole lot of trust in Google to keep that data secure and to not give a copy of it to anybody who I don't want to have copy of it. And whenever we use cloud services, right, and this includes most of the apps that we use on our phone. I gave Facebook as an example earlier. Using YouTube, using Zoom, right? One of the things that I think we always need to think about is, what data am I providing to this company, and how much do I trust them to keep that data private? And I think we both have an individual responsibility to think about what data we want to make available or not. And I think that we also need we also need regulatory responsibility in terms of privacy protections that are written into law, right? Because if you look at any service that you use for free, there's a pretty good chance that the way that they are making money off of that service is that they are using that service to sell your eyeballs to advertisers, right? And that necessarily involves tracking some of what you're doing, building a profile on who you are, the kinds of things that you might like to buy, the kind of shows you might like to watch, the kinds of places you might like to go, and then using that to match you up with advertisers. So it is pretty important in order to think about what kind of information you're giving away before you use one of these services. So I have another question here that is, how do I know if an app that I download on your phone is safe or not? What do you suggest we do before you actually download? This is actually a really hard question to answer because your phone has a lot of stuff that is very private to you on it, right? And it knows things like, where it is, right? It knows, what phone calls you're making. And something that I would recommend doing is that I would recommend going and reading reviews of apps before you download them. You should think a little bit about, what is probably the business model behind this app, right? If I'm using this app for free, is it, it may collect information about me, and is that okay with you? Is this app worth it for that purpose? And lastly, both Android and iOS these days have pretty good permission systems where, if apps want to do things like access your contact list or access your location or access your photos, that needs to be disclosed in the App Store. You can go look at the permissions that the app uses, and then sometimes after you download the app, it will ask, for access to your camera or access to your location. And again, I think, it is worth thinking about whether or not, this seems to be a reputable app maker, and, especially if you're not paying for the app, what is this an app that really needs your camera in order to function, and maybe not use that kind of thing. If it's asking for permissions that it doesn't seem like it needs. Okay, so another question is, do you see the potential of throttling on use of certain internet or communications application based on usage or subscription costs, or will it be considered as a utility? Well, this is an interesting question because there's actually some interesting evidence about this that's come out recently. So you may have remembered, that kind of when a lot of the stay-at-home orders and stuff hit, and suddenly everybody was at home, everybody was spending a lot more time, on video conferences and watching streaming video and stuff. There were actually some of the network providers like Comcast announced that they were going to temporarily suspend their data caps. And they've generally in the past put, they had this pricing that says if you download more than X amount of, data in a month, then, either your usage gets capped or you get charged extra for it. And as it turns out, as they've turned off these caps, that hasn't seemed to have really degraded their networks, right? So the truth is that a lot of data is so cheap to transmit once you've built the capacity, that it makes sense to essentially treat it as unmetered, right? So to treat it as the same price no matter how much you use. There's a lot of business model kinds of stuff around that I probably can't go into in detail, partly just because of the format of the talk and also partly because I'm not an expert on it. But that's a very good question. I'm going to move on. And again, if I didn't get to your question, we'll have one more chance to answer questions at the end. So the last thing I'm going to talk about is how is the U helping to enable some of the change that's going on in the world of computing infrastructure. And so one of the things that is happening is that my research group, the Flux research group, builds testbed facilities that are used for doing research in these areas. And it's used not just by researchers on the U campus, but it's actually used by people around the world. So to help explain why we build these test beds, let me describe a little bit this feedback cycle that exists between research and industry. So, tech companies or companies that make heavy use of technology, they have a profit motive. And so their incentive is to invest in technologies where there is a relatively high likelihood of payoff, where they can put it into a profitable product in a relatively short amount of time. And academic research, on the other hand, if we're doing it right, can be more, can look at riskier things where we don't necessarily know what the immediate commercial applications are going to be, or where we know less about where this research is going to take us and whether or not it's going to turn out to be useful or not. So there's this very nice feedback loop between researchers developing new technologies. Many of them don't end up having commercial applications, but the ones that do tend to be some of the kind of greatest hits of the technology world. The internet is a good example here, right? That was originally a research project. Um, and then the industry will take some of those things, turn them into products, and then we'll also see and then researchers get to use some of those products to build the next phase of what of scientific research. So there's this very nice feedback cycle, and being able to run experiments in many parts of computer science is a critical aspect of this. So let me kind of give you an analogy here, right, for what you need to do research on infrastructure. So if you're starting a business, right, there's a pretty good chance that what you're going to do is you're going to go and you're going to rent office space from somebody else, or you're going to rent retail space in a building that somebody else owns. And this is, how a lot of work gets done. It's similarly, in computer science, it's how a lot of research gets done, by using infrastructure that somebody else is providing. However, if you are an architect or a mechanical engineer and you want to study the behavior of a building as a whole, right, just getting the view of what was inside that one office isn't going to give you a very clear picture, right? You need to have some kind of model of the building as a whole, right? Because you're going to study the electrical system or the structural system, or maybe you're a sociologist who studies the way that people use the spaces in the building, right? So similarly, if you are going to be a computer systems researcher who is going to, wants to understand or change the way that those computing systems work, that storage systems work, that the networks work, then what you need is actually something that's more like a scale model of an entire cloud, right? Where you can sort of peer at all the little bits of it, you can poke at it, you can change it. And so that's why we need to be, as researchers, to be able to have our own cloud environments, as opposed to just using the public cloud that is out there. So, another thing I want to touch on here is that we often, when we think of science and the scientific process, we think of these nice clean test tubes and pretty colored liquids and whatnot. And that is how some science works. But the truth is that, like a lot of science, especially computer science, we run all these experiments and it looks more like a pile of broken glass, right? We try out various things, they don't work, we throw them away, we try something else. Or it takes a lot of iterations in order to get of an experiment or of some development in order to actually get something to work. And so what computer science researchers need, if they're going to do research on the cloud, on the mobile wireless network, is they need this environment where they can build their own cloud, that essentially that they can just sort of build something up, potentially break it, right, and then try it out in a different way. So one of the two big facilities that we provide at the University of Utah, with some partners at other schools like University of Wisconsin and Clemson University, is a facility called Cloud Lab. And as the name implies, what Cloud Lab does is it provides a laboratory environment. Researchers basically get to come and build their own cloud, or their own cloud application inside of that environment. And it's this controlled environment where they're not necessarily serving sort of quote unquote real customers, so they can break it all they want. They can see and modify the parts of the infrastructure that would be kind of a given if they were going to a public cloud and renting virtual machines there. So just to give you kind of an idea of the kind of research that users do on Cloud Lab. So, it's the idea of security and privacy was brought up earlier. There are a lot of people who look into ways that you can construct a cloud such that the cloud provider does not need to have the ability to see or access the data that you've stored on it. People also look at like low latency systems. So if you have something that's interacting with the physical world, let's say, for example, you have a self-driving car that has cameras and other kinds of sensors on it, and you want to be able to get very quick feedback about the direction to take to avoid traffic or whatever. Then you want what's called the low latency system there, where you can get a response very, very quickly. And so designing, that's a whole class of system that requires special designs. Clouds themselves are managed using software. And so people, do research on that kind of software. One of the cool things about a cloud is that because there's a huge amount of storage there, you can write programs and algorithms that deal with large amounts of data. But the kind of the architecture of how you deal with those large amounts of data is itself an interesting research challenge. You look at reliable storage systems, right? I store my photos in Google Photos. I want, I'm trusting Google to do a good job of storing that data without losing any of it. And so people do research into that kind of system as well. And then they do research into the new applications that you can build with these kinds of new infrastructures. So moving from the cloud side to the mobile wireless networking side, another test bed that we have built on campus is called Powder. And Powder is a test bed for experimenting with new technologies in mobile wireless networks. And to really explain to you kind of, I think, what Powder can do, I need to explain a technical concept here called software-defined radio. The radio in a device like your phone or your laptop or your smartwatch is the device whose job it is to take the digital signal that you want to transmit or receive and turn that into a radio signal, and vice versa, to take radio signals in from the air and turn it into a digital signal. And the details of how that works essentially defines a specific radio protocol. So if you've heard, for example, of the different generations of cell phone networks, 2G, 3G, 4G, 5G, each of those is a different radio protocol. Or Wi-Fi is a different radio protocol. And normally these are implemented using computer chips, right? So that chip has a very, very specialized purpose that is kind of pre-built into it, so that it can speak one or a well-defined set of radio protocols. This is great for something like your phone, but it does mean that if you're going to move from a 4G phone to a 5G phone, you need a new chip, which basically means you need a new phone. This is not that great for the research and innovation side, where you want to be able to change these protocols like at will, right? And so you probably can kind of get a sense now what I mean when I say software-defined radio. So it's a device that, instead of being a chip that is for a specific radio protocol, actually allows you to implement many different radio protocols, right? So you have a device that you can program to be, Wi-Fi right now, an FM radio receiver tomorrow, a 5G transmitter the day after that. And so, this is not a concept that we've invented, but it's something that we use a lot of in this Powder testbed. So what we're doing is we're taking these software-defined radios and we're deploying them all around campus, so that basically researchers can build their own base stations. So this picture, this map, it's probably a little bit hard to tell, but the green square is basically surrounding the campus area. The icons on it are different buildings on campus where we've put different devices. And essentially what this lets a researcher do is build their own private 4G or 5G or Wi-Fi network, where it's not serving end customers, right? Nobody is going to walk on campus with their cell phone and have it connect to Powder. But what it's doing is it's providing that environment where it's less controlled because it's over the actual air. However, it is still a closed environment because you can break it, right, as a researcher, because nobody is depending on it for their cell phone service. And again, you get to see and modify parts of the network that would be just a given if you were using, one of the commercial mobile networks. So I thought I'd show you some pictures of what some of this equipment looks like. This particular one is sitting on top of the Merrill Engineering Building on the north end of campus. You can see it's looking out towards the U in the distance. The white boxes on here are a device that it's called massive MIMO. It's a complicated term for essentially meaning that there are a whole bunch of antennas. There's like 128 antennas in those boxes. And you can use that to, when you have that many antennas, you can use it to do some really interesting things like steering beams in radio beams in very specific directions to get better accuracy, or to serve a whole lot of customers using the same frequency at the same time. So, unlike many of our other projects that involve, data centers and sitting in offices, right? This one does send our staff out over all over campus. I believe in this picture, he's climbing the SBS building. That's the big, tall concrete building right next to the library. So we've got, these base stations on buildings all over campus. Because as a mobile, as is implied in the name mobile network, right? You expect some of the devices to be able to move, right? And so things obviously that we've mounted on buildings are hopefully not too mobile. And so our next step in this project is that we are putting these software-defined radios on basically every campus shuttle. So this picture here is looking at the inside of a campus shuttle bus. The little white box that you see sitting behind the seats on the right-hand side there is an enclosure that has several of our software-defined radios on it. And so, pretty soon experimenters are going to be able to experiment with things that, move around campus and have to hand off from one base station to another, or, see different connection qualities as they reach different parts of campus. So this Powder platform then provides what we call a city scale living lab. So by city scale, I mean that it's, the campus is a pretty large area. We're also hoping to be able to expand in a couple of years to the downtown Salt Lake City area as well. And it's a living lab in the sense that, it is, it is a real environment that has, real interference from other sources, real reflections off of buildings and things that block signals, right? Which are messy, but also are what you need if you really want to verify that your protocol is going to work in a living, real environment. And then it allows researchers to experiment with new radio protocols and applications. I'm going to talk a little bit about the research that people do, and then I'll take questions again. So again, good time to type in some questions. So what do people do with this, right? Given these radios that they can control in a lot more detail how they work, and is out in this living environment, what do they do, right? So one thing that they do is they look at new radio protocols. So they look at, so of course, as we move our mobile network from 4G to 5G, obviously that's a thing that a lot of people think about and wonder about and experiment with. But also experimenters, look at protocols that are designed to do things like connect large numbers of devices that transmit only every once in a while, right? So things like my sprinkler controller, right? Or, sensors that are scattered about in an environment, because really the existing mobile networks that we have were designed for things like phones that have kind of constant connection to the network. As I mentioned earlier, like faster is a large part of this, right? Using some of those higher frequency, using new mechanisms to encode data in the radio frequency spectrum to get more efficiency. I mentioned using those large numbers of antennas to reach a lot of different, like a lot of different users in the same spectrum at the same time. And then of course the new applications that you can build on top of a network like this. And one of the interesting things, by the way, that I think is probably worth mentioning is that the FCC has created what they call an innovation zone in Salt Lake City that makes it easier to get licenses to experiment with different kinds of radio protocols. And we're one of only 2 places in the country where that's possible right now. So this is actually one of the best places to do research in wireless communications right now. So thank you. That's the end of the prepared talk that I have. I'll take some more questions. If you have more information about the particular facilities that I talked about, cloudlab.us and powderwireless.net are the two the websites for the two testbeds that I talked about. My research group is at www.flux.utah.edu. And if you have anything you want to follow up with me, any questions to ask, you can contact me directly at ricci@cs.utah.edu. A couple other plugs. If you liked the portion of the talk where I talked about some of the internet infrastructure and the pieces around us, there's a really great book that's very accessible. It's written for a general audience called Tubes by Andrew Bloom that covers a lot of that stuff. And it's also important, I think, to say that those testbed facilities that I talked about are funded by the U.S. National Science Foundation, which means that they are available for free to all research, the whole research community in the United States to run experiments on them, whether they're at the U, whether they're someplace else, whether they're at a big school, whether they're at a small school. Okay, so with that, I will finish off with some questions. We got a comment from someone who is an older alumni who apparently used Fortran on punch cards for the UNIVAC at the U in 1973. And actually, one fun fact that I'll mention about this, so this is an old computing technology that was around quite a while ago. My guess is that you probably used those punch cards in the MEB, the Merrill Engineering Building in the third floor. That same data center is actually now where a bunch of the equipment for our Powder and Cloud Lab facilities. So we still use these data centers. Another interesting tidbit that some people may be aware of, but some not, is that the University of Utah was actually the fourth site on the ARPANET, which was the predecessor for the internet. And we were the first site outside California. So we actually have a very long history of network research and being kind of on the forefront of computing infrastructure. Okay, so another question here is, what are the power demands for the radios, and can they be small enough to be self-powered, e.g. with solar and batteries? This is actually a really interesting question about those software-defined radios. One of the reasons why your cell phone uses a chip that is specifically designed for LTE or for Wi-Fi is that the software-defined radios, while they're more flexible, also are more power hungry. So everything that we have is powered when we can off of just the utility grid power. The ones that are in the buses are powered from the bus's power system. So we generally, the devices that we deal with, generally we do not, they're generally power hungry enough that they do not run off of batteries. There are some software-defined radios that are lower powered, but in general, dedicated silicon is a more efficient way to run a radio protocol, which is why not every radio in the world is software-defined. Okay, interesting question here. How has your research changed because of COVID-19? One interesting aspect of the facilities that we provide, Cloud Lab and Powder, is that they're accessible over the network from anywhere. So people who are accessing Cloud Lab are generally accessing it in exactly the same way they were before. And in fact, one of the things that we typically see is when the school year ends, the usage of Cloud Lab drops significantly because people are off, they've graduated or they're doing internships or whatever. And this summer, it's actually stayed incredibly high. And I think that's because people are stuck at home and they're, and the kind of research that we do can actually be done at home just as well. We are doing a few things to try to help support other researchers who are doing research in COVID-19. So for example, we're supporting somebody who works more in the social scientist, as a social scientist who is studying Twitter and the way that people react to official announcements about COVID-related stuff. That's something that I would not have been involved in a few months ago, right? But it's obviously a very interesting topic of communication right now. And I think, one thing that I think COVID has shown is how important it is for a lot of these services that we use to be able to scale up quickly, right? So I don't remember the exact numbers, but if you look at the numbers for the video conferencing services like Zoom, what you see is that they got 10 times or 100 times as many users, within the space of, a few weeks, right? Because all of a sudden everybody was at, video conferencing instead of meeting in person. And one of the interesting things about the cloud that the cloud promises is the ability to essentially rent only the resources that you need only when you need them. And so I think one of the things that we've seen in the last couple of months is that many of the companies that do a good job of using cloud services to scale up their capacity very, very quickly. Some of those companies have done very well, right? While others that were, perhaps not as adept at using as having those kind of scaling technologies may not have done so well, right? They may have had more outages or had more kind of growing pains as they grew into the current world. And so obviously scalability and reliability are a big part of this. So I'm going to take one more question because we're just at about an hour here. That question is, what are the compute units you use in Cloud Lab? So they are servers. Essentially, they are servers with processors in them that are not entirely unlike the processors that you might have in your desktop or laptop. They are more powerful and they have more they have more computing cores in them and they run at higher clock speeds, but essentially it's the same basic technology. And we have them in, I mentioned the use data center that is downtown near the 9th South I-15 off ramp. We have a bunch of servers in that location. We have them in data centers that are owned by University of Wisconsin-Madison and Clemson University, because real clouds are in fact distributed over the world, and so our experimental infrastructure is too. Well, thank you very much. I really appreciate your attending this today. I hope that you found this valuable. And again, if you want to, you're welcome to visit any of the URLs that are up on this slide, or to email me directly if you have any questions that I wasn't able to get to in the talk today. So thank you very much, and stay healthy and stay safe.